Hello everyone, and welcome to this, the latest in the series of TCCA Critical Update webinars. My name is Tony Gray, and I'm Chief Executive of TCCA, the global representative body and advocate for open standards for the critical communications sector. Today's webinar focuses on interworking between mission-critical broadband and currently deployed LMR/PMR systems. In case you're wondering about the slight modification to the title, it's to avoid any misunderstanding of the word legacy, which is in no way meant to imply obsolete in the context where the presenters are referring to existing networks. The session will be presented by Harold Ludwig, Chair of TCCA's Technical Forum, Michelle Doubts of the Norwegian Directorate for Civil Protection, Dave Chater-Lee, Fellow of the Technical Staff of Motorola Solutions UK and Vice Chair of ETSI TCCE, Bill Yankee, Senior Standards Engineer with FirstNet in the USA, and Ari Toivonen from Erillisverkot in Finland. We have attendees from around the world, so we're looking forward to an informative and beneficial experience for everyone. Please submit any questions you may have during the course of the webinar using the questions pane on the right of your screen. If you're on a mobile phone, this appears at the bottom of the screen. If there's time immediately after the presentation, your presenters will answer as many as possible. And if there are any that don't get addressed during the webinar, they'll be responded to afterwards. The presenters' slides will be made available after the event, and there'll be a recording of the webinar available online, as well as a document containing all the questions and answers. So I'm now pleased to welcome your presenters for today, starting with Harold Ludwig. Harold, over to you.
Thank you, Tony. I have the pleasure to start and to introduce the agenda with you. So I will do a few setting the scene slides, what's interconnection, what's interworking. Then you will get a presentation from Michel about his experiences from interconnecting systems. Then we will have a presentation from Dave about the standardization in 3GPP for the interworking. And Dave will continue and explain to us what is done on the Tetra side. Then there will be a presentation from Bill about the same standardization or similar standardization activities for P25. The last presentation will be from Ari about testing and conformance. We will have about an hour for these first 6 parts, and then we will have half an hour for questions and answers. So let's jump into the first part, introduction to interconnection and interworking. These two terms are very often used not in a consistent way. So just to clarify, what is interconnection, what is interworking? Interconnection is the communication of users across different 3GPP mission critical systems. So in this case, you have a system A with a user A1 on one side, and you have a system B with a user B1 on the other side. And if you interconnect these two systems together, then user A1 is able to talk with user P1. There is another flavor of interconnection in the way that a user from system A can migrate to system B and connect to system B and get mission critical services from system B. So this is interconnection. And just to be clear, today's webinar is not about interconnection. So this is out of scope of this webinar. What we will present is interworking. Interworking is connection of a 3GPP mission critical system with its users and devices to other systems, non-3GPP systems. This can be Tetra systems, GSMR systems, P25 systems, or other land mobile radio systems. And to connect them, there is this so-called interworking function. The standardization activities are split. So 3GPP is standardizing the so-called IWRF interface, and other organizations are looking into defining, standardizing the interworking function. So for Tetra and for GSMR, this is ETSI, the European Telecom Standards Institute. And for the P25 and land mobile radio systems, this is ATIS, the US-based standardization organization. Okay, so that's to interworking. We will go into the details in the next presentations. But before we go into the interworking, I will come back to interconnect, but not interconnection of broadband systems, interconnection of narrowband Tetra systems. Because some years ago, 3 countries, the Nordic countries, started to interconnect their Tetra systems. So Norway, Sweden, and Finland have connected their Tetra systems. And our next presenter, Michel, was involved in this project, and he will tell us about his experiences, which are not only technical, but also on other levels. So over to you, Michel.
Thank you, Harald. Good afternoon, everybody. My main topic for today is international collaboration of public safety networks in Scandinavia. The way our users work with their own communication equipment across national borders has been an item within Tetra since it was still called Trans-European Trunked Radio, migration with your radio into another Schengen country. Traditionally, there has been collaboration and communication across borders in the north. The bullets on this slide list up some examples. And to make sure that we are competent and able to help each other, the organizations in the 3 countries train regular with each other to test the logistics, the processes, the chain of command, how to support in international scenarios on or close to the border. On the next slide, we see that the inter-system interface as a standard to connect Tetra was available for several reasons, but not achievable. Think national rollout in 2009, the investment costs. Commercially as a product, it was not available, and there was no support to develop or implement it in the most European countries. As a start, between Norway and Sweden, we made a back-to-back solution to support connected talk groups in the Swedish and Norwegian networks. As shown on the slide, Norwegian and Swedish provisioned radio terminals are connected. So per each network, a radio supports a talk group in each of their own networks. This is of course a very limited solution, but end users with their Tetra terminals could communicate without using GSM or fixed telephony lines. Back-to-backs were also used before us in the Netherlands, Belgium and Germany, Denmark and Sweden. On the next slide, we see on bullet 1 that by the time in 2003 up to 2007, ETSI specified the standard. In the meantime, several trials with the 3-country pilot, an ISI in Romania, an ISI between Sweden and Germany, were held and trialed, and end users provided input for interoperability and scenarios for implementation. To sum all our efforts up, the TCCA published a white paper on ISI in 2010 that summed up the actually challenges we had with ISI. Luckily, during the national rollout, the will to connect 2 major public safety networks were done by Norway and Sweden, and that put things into speed. At the same time, a European Union funded program was started to investigate and make pilots for connecting different networks. A demonstration for this EasyTech project was not a pilot as such from our side, but a full-blown exercise with 2 connected live networks, where we have real radios migrating with all specified voice and data services like group calls, emergency calls, SDS configured. The acceleration has begun, as we see on the next slide. Norway and Sweden made the ISI interface applicable by going with our vendors Airbus and Motorola Solutions step by step to the ISI specification as delivered, and we planned to make it fit in our situation. It was a guiding principle to keep it simple, make it work, don't do difficult stuff. Look and feel as home whenever as possible. So with the help of a lot of end user support in the form of participating agencies, we created a shared involvement in subgroups for procedures, user cases to make all these technical challenges into daily routines. During this time period, we had several big gatherings with end users, technical staff, projects to discuss and exchange ideas of possible ways to mold the technology towards our end user needs. As such, the deployment of ISI opened the borders for public safety users, literally. Not only the infrastructure, but new adaptations were made on the radio terminals and the presentation and interaction with foreign radios in your command and control centers. Just making it fit and work by going through these 6 steps several times and repeating, we took the deployment of ISI a step further every time. So on the next slide, we are 4 years further in time. And by this time, we had already an EasyTap demonstration in Meråker, Trondheim. This is on the picture on the left. Meråker is an area in the middle of Trondheim, quite busy for commuting between Norway and Sweden. We decided to do in this middle part of Norway with Sweden a big exercise with a traffic accident on a small road. The exercise demonstrated the live uses of ISI for public safety users mapped into their routines. It was an early start, but people were so happy that they actually could migrate with the radios and communicate in the visiting country and back home. The picture in the middle is from an exercise called Barents Rescue 2019 in the middle of the northern part of Sweden called Kiruna. By that time, we had 3 swimmies from Norway, Sweden and Finland connected. The lessons we learned in the period between these exercises and the daily users is that the end users know they can communicate via a network service within Nødnet, Rakel or Virve. It should not matter which Tetra network is servicing you. This is illustrated on the right. That bar shows the best serving signal strength and registration on the 3 networks in the northern part where Norway, Sweden and Finland have shared borders. And this specific measurement shows a tour from Skibotn in Norway via Kilpisjärvi in Finland to Kautokeino in Norway, which is a road via Finland along the Swedish border, where, as we found out, the Swedish network provides in some cases a better service. This scenario illustrates an improvement for hosting Finland-Norway talk groups in the Swedish network, because the Swedish network provides best coverage in the area for users from Finland and Norway. This header shows shortly where ISI is actively deployed. So between Norway, Sweden, Finland, Norway, Finland, Sweden, and Finland, Norway, Sweden, we have concept tested and we have integrated interworking between the networks. An extended fleet map structure has been tested, and now we think about getting this experience into new standardized solutions that could help us in the near future. Regarding the interworking, our ISI experience and standards are fed into this process to adapt bridging functionality between Tetra and 3GPP mission critical systems. Looking at how the ISI has connected and integrated services for our end users, this could benefit the future interconnection on the next generation of public safety networks, like using services in the visitor network or supporting a feature like dynamic migration. On my next slide, this shows basically what is the scenario per today. Everything that is in blue shows up what is there available right now with our networks, our interconnections with the 4G networks, and the plans to look into the future with interworking with Tetra towards mission critical systems. The journey that I presented in less than 7 minutes to you shows that it's possible to continue with new challenges towards 3GPP, since in addition to the standardization process, we add the non-technological part, be it all the necessary agreements, aligned procedures, communication schedules, and processes and operations that has been made during the deployment of ISI. This is not difficult, but you need to do it, and it takes a lot of time. The webinar from last week updated the status from operators' perspective in the Nordic countries. We are all in the process of defining the planning for the next generation's public safety networks on 3GPP. Today, we even have some pilots started with interfaces towards 4G networks to have speech items into our Tetra networks. Although this drawing may look complex, we all know that the reality is even more complex. On the next slide, I would say a thank you, because this trip has not been made by me only, but also with Magnus and Peter Weiko, colleagues from Sweden and Finland, and the shared effort from the beginning from the Swedish and Norwegian Directorates for Civil Protection, as Werklot, and many vendors, and not least the TCA Technical Forum and the ISR Working Group, and many others who help make this work and use technology daily. Remember, a border is not a boundary, it's a passage. So on the next step, I will present further to David, so please go ahead.
Before we go to Dave, thank you, Michel, but you've provided us a short video which demonstrates the cross-border communication, and which I'm going to show now.
Oh, I forgot. Yes, please do.
Yeah.
The video will show a migrated Norwegian radio in Sweden and Finland calling each other via the other networks.
1, 2, 3, 4. 1, 2, 3, 4.
Okay. 1, 2, 3, 4. Registered on Raquel. Registered in Finland. Can you answer it?
1, 2, 3, 4, 5.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
Kjempegreight.
Okay, I will go back to the presentation screen, and we'll hand over to Dave now. Dave, please.
Thank you, Harold, and of course, Michel as well. So I am going to talk about the work that's been done in standardization to enable this interworking between 3GPP, mission critical systems, and LMR systems. For the first part of the presentation, I will describe what we have been doing on the 3GPP side, and then in the second half, I will take a look at what's been going on within the Tetra standards. So if we move on to the next slide, please, Harold. This is just a quick recap on 3GPP mission critical systems. The work's been going on in 3GPP for some years now to standardize mission critical applications such as press-to-talk voice, video, and data. And the standards currently allow this operation over a 4G LTE network and are being extended to go to future technologies such as 5G. The first release providing the speech service, mission critical push to talk, was completed in 3GPP release 13, which was in 2016, and then video and data were added the following year in release 14, 2017. The interworking specifications with land mobile radio, which was mainly aimed at Tetra and P25, was first worked on in release 15, but the protocol side of it was completed in this latest release, release 16, which was completed in June of this year. It's been a steady progression. Functionality is being added all the time, and so further enhancement is going on in release 17, and this is the first time that we're starting to look at the needs of the rail industry for interworking with GSMR. We provide specifications for speech services, MCPTT, and for the short data service part of MC data. Now on the next slide, I will give a little bit more detail about the facilities that are being provided. Clearly, group call is one of the most important functions within a land mobile radio network used in the mission critical environment, and also within the 3GPP side. So the requirements for group affiliation, in other words, joining a group to take part in communications, and the group calls themselves are supported. We also have support in the standards for group regrouping, merging groups together, where this is supported by the land mobile radio system. And some systems may and some systems may not support this. In fact, we've been extending the procedures for group regrouping and interworking because we've extended the procedures within the mainstream mission critical communications with a newer procedure introduced in release 16. We support individual communications with an individual call or private call, same thing, and users can originate or terminate the call in either of the two types of system. Either group or individual calls can be made into emergency calls, which then treated with high priority, both on the 3GPP side and on the interconnected land mobile radio side. Within a call, we have to deal with transmission control, decide who gets to speak next if multiple people are requesting that, and that then introduces prioritization. It introduces transmission interruption if somebody with a higher priority needs to interrupt somebody with a lower priority, even if they're on the other technology system. And we also have support for call queuing, where this again is supported on the land mobile radio side. We support short data messages, and again they can start and finish in either type of system, and also they can be sent to groups as well as to individuals. And finally, recognizing the needs of the community that this is serving, we will support fully end-to-end encrypted communications as well. The land mobile radio systems targeted were initially Tetra and P25, and there is also additional support for analog FM networks as defined by some TIA standards. We don't support other technologies yet, although, as I said before, work is beginning to introduce GSMR as another standardized interwork technology. But the way the specifications have been made in 3GPP in a very generic manner, it will be quite easy to add further technologies if there are user requirements for these that come along. Clearly, 3GPP is a user-driven organization, and so further technologies would have to come in through the user requirements group SA1 to then filter down to the downstream groups to do that. We specifically do not support MC video. Video is not usually standardized on land mobile radio systems. They simply don't have the bandwidth for it. And we don't support the larger types of file distribution. Again, if you look at traditional land mobile radio deployment, the IP packet data services are nearly almost entirely mobile to a host on the fixed side rather than mobile to mobile. And so we assume that the mobile unit will continue to communicate with applications in the fixed network, and something on the fixed side may be able to communicate where information needs to be shared between users on both systems. So that gives you an idea of the facilities. On the next slide, I will look at the behaviors that we will experience, because what we did not want to do was introduce something that would be either a complex effort in standardization or indeed difficult for users who are trained in the art of communications to use when communicating with the other technology compared with communications within the same technology. So, for example, if there is an individual or a private communication taking place entirely on the 3GPP defined side, as far as the users are concerned, the communications look very much as if it's communicating with another user on the same technology, when in fact the interworking function is mapping this to a land mobile radio system, for example, Tetra. And for the land mobile radio system, for example, Tetra users, as far as they're concerned, the 3GPP users simply appear to them to be other Tetra users within a connected system. So the behavior changes are minimized and the user changes are also minimized. To minimize the standardization, clearly, we needed the IWF to operate as much as possible like another mission critical system. So from the 3GPP point of view, our standards for interworking are based on those for server to server communications. So if we now look a little more detailed at the reference model on the next slide that we have on 3GPP, we've standardized the functionality of the interworking function by means of three defined interfaces or three defined reference points. One of these is for the speech server, the MCPTT server to IWF. The second of these is for MC data communications, and so standardizes the MC data communication functions with the IWF, IWF being the interworking function. And then the third of these looks at the other associated servers you need to provide a mission critical service, and provides functions like group management, configuration management, security management, and so on. Now, the specifications define these interfaces. They don't specify the behavior of the IWF itself. We put that out of scope of 3GPP standards, but its behavior is obviously specified by implication because we need to understand how it behaves in response to these interfaces. But so the IWF behavior is sort of partly in and partly out of 3GPP specifications. Overall, the model views it as part of the land mobile radio system. There is a small variation of this when it comes to security, because the 3GPP security needs to be terminated before transmissions are moved into the associated land mobile radio system. And so we assume that the security gateway, which is fully defined within 33180, which is the mission critical security specification, we assume that is part of the IWF functionality. As I've said previously, the IWF is behaving as if it's another mission critical system as far as that's possible to minimize the impact on existing MC systems. And as I also said on the previous slide, the user equipment on the mission critical side shouldn't need to see any changes for interworking, except in the single case where we want to run end-to-end security fully from terminals on the land mobile side to the mission critical UEs. And in that case, then the mission critical user equipment does have to understand the vocoder, the speech coding that's used on the land mobile side, and the encryption mechanism. So that really is the overall description of the reference model. If I go to the functionality then that we require on the next slide to fulfill this, there are things we need to do to enable this fairly seamless intercommunication between the two different types of systems. First of all, we need to translate the identities. Land mobile radio identities tend to be based on binary hexadecimal types of numbers, numeric in their format, whereas on 3GPP side, we use URIs, which tend to be alphanumeric strings. So clearly we need to translate between these two in some way. The security aspects need to be dealt with. The security doesn't flow from one system to the other simply. The 3GPP security takes quite a lot of bandwidth if you were on an LMR system, so we couldn't flow that across. And similarly, the LMR mechanisms are slightly different to those on 3GPP side. So we need to terminate those, and we need to provide key management where end-to-end security is provided fully end-to-end between the UEs and the LMR users. For the majority of calls, with the exception of this end-to-end encrypted case, we'll need to carry out transcoding in the IWF so that the wider bandwidth vocoder used on MCPTT, AMR wideband, is translated into whichever vocoder is used on the land mobile side. And if we do allow the land mobile vocoder to be carried right the way through to the MCUE, either for end-to-end encrypted use, or if somebody simply wants to maintain one vocoder throughout the call, we need to negotiate the use of that speech codec as part of the call setup signaling. So these are things that we need to do above a normal server-to-server interface within MCPTT and the other services. Similarly, where short messages are exchanged, the formats will be slightly different between the two services, so we need to do anything necessary with that. And where applications are built using short data on the land mobile side, such as location information, if that's needed to be carried across the IWF, we need to do some support for that. There will probably be further functionality needed to support the railway applications, but as I mentioned, this is very much work in progress. So this is really a very fast overview of the IWF. On the next slide, I just give one more detailed description of the one particular important service, namely group communications. So we have to make some adaptations because we're dealing with a different technology on the other side. And one of the differences between the way connected land mobile radio systems can operate, such as Tetra to Tetra using the inter-system interface, is we don't necessarily pass all of the group affiliation information across the ISI. Instead, we might tell the other system we need to use this group, but we're not going to tell you about everybody that wants to use it at any particular instant in time. So because of that existing behavior, we've carried across something similar onto the mission critical side, and we've allowed each LAN mobile radio user's affiliation to truly be sent through to the IWF and on into the mission critical system, or we've allowed the LAN mobile system to simply affiliate once on behalf of all of its users. The IWF will pass a single affiliation onto the MCPTT server, and then the MCPTT server will pass group call information back to the IWF, and it's up to the IWF and the LAN mobile system to distribute the information to other users. So this is one area where, because of the behavioral differences of the two systems, we need to make some adaptation in the way the MC system works, and the IWF will have to do some adaptation in the middle. So that was just a quick, brief dip into one of the subjects. For my final slide on this subject, I've simply listed the interworking specifications that are relevant, both the stage 2 specifications that describe that functional model and the overall information flows that you see, the overall message flows, and then the stage 3 protocol specifications that go into the next level of detail of the protocol and the security document. So those are obviously there in the handout slides if anybody wishes to look at those later. Now I'd like to move on now to my second part of the presentation. If we can move the slides on, please. So I'm now going to look at this from the Tetra side. So if we go straight into the first slide, where I'm going to pick up the reference model once again, but now I'm going to look at it from the Tetra side. I've mentioned already that the interworking function is considered by 3GPP to be out of their scope, to be part of the LAN mobile system, and the interface itself is what is specified from 3GPP. We took the decision within the Tetra community early on that actually we would not invent any extra interface on the Tetra side between the IWF functionality and the Tetra SWIMI, the switching and management infrastructure functionality. We would simply build the IWF into the SWIMI, and the specifications would then simply standardize the behavior that the mobile station sees and compares or explains how interactions between the mobile station on the Tetra interface then result in interactions on the IWF interfaces as specified by 3GPP. And that simplifies the specifications somewhat. It also means we don't need to worry about loss of functionality, for example, if there was a third interface sitting in the middle doing some other function. So this is the specifications that we are providing, this interface between the air interface and the interaction between that and the 3GPP IWF interface. If we go to the next slide, we'll look at the functionality that will be provided on the Tetra side. Very much, as I said, from the 3GPP perspective, the Tetra mobile station will consider users on the 3GPP MC system to be further Tetra users sitting on a different Tetra system where there is an ISI involved. The involvement of the ISI means that the addressing that the Tetra mobiles will use will be the extended addressing that you need to deal with inter-system communication on Tetra. But the 3GPP system will simply appear to be a different Tetra system identity, and the mobiles will appear to be identities within that. We intend to follow the functionality adopted by the ISI as far as possible. So that means a slightly different approach for group calls, in that ISI group calls today are considered to be local group calls. We don't use inter-system addressing for group calls. We simply use a local group on the Tetra system when we're communicating with a group across ISI, and we will carry that behavior over into the interworking functionality as well. As I stated a little while ago, the IWF has to manage how the identities are represented in each system. We haven't been prescriptive on this. We think the majority use will be a configuration table where there will be a list, if you like, of the 3GPP mission critical identities and how those map to identities seen on the Tetra side, and Tetra identities and how those will be translated to identities seen on the mission critical side. But by leaving it open, if somebody wishes to implement an algorithm, for example, show the Tetra identities up as a sort of URI, 1, 2, 3, 4, 5, 6 at 7, 8, 9, 10, that is possible. They would have to work out the translation of the URIs in the other direction as well, but that's something to be left for implementation. In general, the speech transcoding will be taken care of by the IWF, but clearly if we need to use end-to-end encryption using the Tetra vocoder and the Tetra encryption mechanisms, or indeed if we want Tetra ACALP to take place, then we'll also allow the IWF to negotiate the use of ACALP through to the far side and to deal with key management messages where end-to-end encryption keys are passed across to the other system. My next slide takes a quick look at deployment scenarios for Tetra and mission critical systems. We could see one-to-many, many-to-one, or many-to-many deployments of Tetra and mission critical systems. So our specification will not preclude, will not prevent, will not do anything to stop any of these different types of deployments. The specification simply looks at a single instance of the interface. When it comes to deployment, then multiple can be deployed. In fact, multiple can be deployed between the same pair of systems, the same Tetra and MC system, if that was wanted for resilience. We just leave it to the implementer to decide which communications are sent over to which interface. We treat that as out of scope of our specifications. My next slide takes a quick look at the security aspects. As I mentioned earlier, the security side is something that is very important in the mission critical community, and we do need to ensure that the interworking specification takes this into account. The security mechanisms that we deal with, authentication is dealt with separately on each system. A user authenticating to the mission critical system, a Tetra mobile station authenticating to the Tetra system, they're both local transactions, and the IWF and the interworking will have to trust that they have been carried out satisfactorily on each side. That's not something we can carry across the interface. Where each system has its separate security mechanisms that don't carry over, the 3GPP encryption mechanisms are one example on one side, Tetra Air interface encryption as an example on the other side, those will get terminated in the middle by the Tetra system or by the IWF. For users that have Tetra end-to-end encryption, we will allow the IWF to terminate that if that's what a user wishes to do, to avoid any translation needed on the MC side and any understanding by the MCUE of Tetra end-to-end functionality. But the specifications will also allow the Tetra end-to-end encryption process to be carried fully end-to-end to the MCUE, so long as the MCUE is able to cope with that functionality. So security will permit fully end-to-end operation where that's desired. My final slide is just a listing of the specifications that are involved. As you will see, we have been looking at this for some time. We have published 2 studies already from ETSI in 2017 and 2018, which looked at some of the issues, both for the overall interfacing and then the security aspects of that. The protocol specification that's being standardized now is taking place in Working Group 4, of which I'm the chairman. We're basing it on the 3GPP release 16 specifications, and we intend to complete this sometime during 2021. Already, to permit the speech transport to work fully end-to-end and the encryption process to work end-to-end, we've already published the specification for that information transport, and the transport information has also been registered with the Internet Numbering Authority, so that's available already. Finally, from the TCCA's point of view, the security group in the TCCA has also been looking at the security policy and other procedural aspects to give guidance on this. And from the SFPG, the security group, we published a recommendation at the end of last year, which gives some advice and some guidance on users that may wish to implement Interworking for some of the things that they would wish to do in terms of security. So that completes my presentation. I'll now hand over to Bill Yankee to look at the equivalent interworking between P25 and the MC systems. Bill, over to you.
Thank you, Dave, and hello, everyone. Yes, Dave has done an excellent job in covering the technical aspects from the 3GPP side and from the Tetra side, and it's not a whole lot different in North America for what we are doing. You know, the technical part is very similar to what Tetra is working on, a few differences. So I'm going to focus a little bit more on what we're actually doing in North America to standardize this interworking interface. On the next slide, I'm going to cover what organizations are involved and what we're working on. So 2 standards organizations are working on interworking standards. First, there's ADIS, which is the North American organizational partner of 3GPP. And ADIS sometimes works with TIA, which is the Telecommunications Industry Association. We have developed a joint committee between the 2 organizations called JLMR-LTE, and that committee is developing the Stage 2 architecture specification. And then we have TIA-TR8, which is the Mobile and Personal Private Radio committee under TIA, and they are the committee that has defined P25, which is underneath the TIA 102 suite of specifications. And TIA-TR8 is defining what we call the Stage 3 protocol. So we've adopted some of the 3GPP nomenclature for Stage 2 and Stage 3. So those are the 2 organizations. What is the JLMR-LTE committee doing? We've unofficially organized our work in phases, and when we complete a phase that has some subset of functionality, we hand off to TIA to do the Stage 3 work. So we've completed phases 1 and 2. We're doing phase 3, and phase 1 and 2 support a fairly robust set of P25 trunking features. And when we get to phase 3, we'll hopefully support all of the common P25 function trunking features and a subset of P25 conventional. And then TIA, of course, is working on the Stage 3. They've completed the Stage 3 for phases 1 and 2, and they're currently in the process of publishing specifications that support phases 1 and 2 right now. And actually, voting is taking place this month. So we haven't published anything yet, but we're almost there. The ADIS Stage 2 architecture spec, we haven't published that yet either. We've just been handing it off as it's getting filled in. So we plan on continuing development through 2021, completing P25 conventional radio, and hopefully including some analog FM conventional. We'll see how far we get. So please, the next slide. I don't want to get into this much. It's a little boring, but this is how we've mapped our architecture. Dave has covered this in detail on the IWF side, 3GPP side, and we've just mapped this in our architecture to some reference points for TIA 102, which is P25, and TIA 603, which is the standard for analog conventional. So on the next slide, I want to talk a little bit about what it looks like for FirstNet. Of course, you know, we have FirstNet is developing a nationwide broadband network. So in some sense it's a little simpler than the situation in Europe and other parts of the world, but in fact, it's also more complicated, and I'll get to that in a minute. This is fairly a simple diagram of what it looks like for us. Of course, we have the IWF, which we've talked about in detail, and 3GPP is defining that side. And on the LMR side, we have P25 systems, which are both trunking and conventional, and then we have conventional FM, and we have ADIS and TIA working on that. We've settled on in our architecture, and in Stage 3, we've decided that the P25 interface of choice is the ISSI, which is the inter subsystem interface for P25. So on the LMR side of the IWF, it's going to look like an ISSI node, a home serving RF subsystem. And of course, on the other side, it looks like a 3GPP MC server. The analog side, for analog conventional, we don't know what we're doing yet. We haven't really looked at it. It could be ISSI, but that's going to require some extensions there. It could be the fixed station interface or anything, but we haven't gotten around to it yet. Okay, so if we can move on to the next slide, please. Go ahead. And this is, you know, 95, oh, I'm sorry. Yeah, we can skip that last slide. That's fine, because it just talks about features that we're going to support, which is the usual that everybody is looking for to cover 95% of what users do every day. So what is our current climate in North America? Well, it's the The problem we have here is that we have states and counties and towns and villages and a large area to cover, and we have P25 systems, phase 1 and 2. We even have some old EDAC systems out there and OpenSky systems. We even have a few Tetra systems and NXDN systems. So we have a large number of disparate radio systems that are all using different technologies. Hopefully P25 is the majority of them, but we still have a lot of analog FM systems out there. So all of these systems may potentially want to interwork with FirstNet. So that creates our first problem. Of course, cost is always an issue, and everyone has investments in their current system and in their current devices, and they have to always take that into consideration when they're thinking about how to evolve and migrate their systems to the next big thing, which is MCPTT. So while waiting for standards to develop, which always takes some time, people have decided that they needed PTT now, and there's been a fairly broad adoption of disparate commercial PTT systems, so that we have that issue to deal with. And because we already have commercial PTT systems out there in use, and we're only now starting to deploy MCPTT 3GPP standardized system applications. Since they already have that, people said, well, I need to connect it to my land mobile radio system. So where's the standard? And, well, we haven't quite finished it yet. So, okay, well, we'll have to have some other solutions. So other solutions have been deployed already to fill the void in lieu of standards. Two of the main ones that are out there is ISSI, of course, has been standardized for at least a decade. So there are quite a few ISSI installations around our country, and people have connected that into existing commercial PTT systems. And so it looks a lot like what we're trying to deploy here, but and there's some differences, and of course it doesn't follow the standard. It's close. So those people that have those installations are going to have to, upgrade eventually to get something that's standards compliant. And then we have this thing called radio over IP. You may be familiar with that. It's a fairly simple solution. It's more like it's simply donor radios on each side, or a UE on one side and a radio on the other, connected with a VoIP connection between them. Fairly cheap and dirty, but it works. It just doesn't have all the features that you need. So we have this situation where we have lots of systems out there that are already deployed. We have lots of interworking already happening, none of which is to the standard, and the standards aren't complete. So we have a large job ahead of us to get this situation under control in the long run, but hopefully things will shape up as the standards are completed and published. My final slide is just talking, you can go ahead and scroll down, just talking about the differences between radio over IP and ISSI. Of course, we've chosen ISSI as our stage 2 architecture solution, and stage 3 is now publishing addendums that talk about how the ISSI has to change for interworking with mission critical broadband systems. So that's where we ultimately want to go. Of course, the ISSI is more expensive. It requires backhaul, but it supports all the features that you want. So that's the way we've taken the standard in North America, and that's the way we want everyone to move in the long run. But in the meantime, we have radio over IP, which is filling a gap. Maybe that will be the solution ultimately for analog FM connectivity, but we don't know yet. But that's the situation in North America, and that's the last slide I have. And now I'd like to hand it off over to Ari.
Yeah, thank you, Bill. My name is Ari Toivonen. I come from Edellisverket, and I'm going to talk about testing and conformance. And I'm mostly going to approach it from operator's point of view, as covered by all the previous presenters. And you probably have realized that we are connecting networks together, and that's what operators do. So next slide, please, Harald. So testing. There's lots of testing you can do and you should do when you're implementing new products and features. But from our point of view, and within this context of this webinar, the two kinds of testing which are mostly relevant are conformance testing and interoperability testing. And conformance testing is a formal testing process which is typically done using a test tool, testing a terminal against test tool, checking that it works, etc. But thinking of this IWF testing, do those tools exist? Can you, even if there's a tool that tests a mission critical network working over IWF, is there one for the LMR side, and so on? And if someone would come to you and say, hey, I developed a brand new testing tool for you, and this proves everything, would you really trust that thing? Or is this just a nice tool, but actually doesn't provide you anything? That's something worth considering if you're an operator and looking at this area. And what we actually, in the end, the ultimate goal for us is interoperability. And there, if you start thinking about it, there's multiple LMR systems, P25 Tetra, even analog, GSMR in future, and multiple mission critical suppliers out there. And if you would want to do a complete set of interoperability testing, you had lots of combinations be tested. But then on the public safety operator's point of view, maybe excluding cases like North America, you typically talk about one LMR network and one mission critical supplier. And that's the combination you care about. It's nice that someone tests all the other things, but you really care about only one combination. So there's potential that people do lots of testing and not that many people are interested. And where should you do this testing? Especially interoperability testing, you'd really want to test against your live network today when you bring in the new service to be linked to. But testing with live net environment is always challenging. In the worst case, you manage to actually break something in a live network, and you really don't want to do it in mission critical networks. So if you have a test environment, or if you can reasonably, with a reasonable cost and other effort, build one, I'd really recommend you to use a test environment to do these tests, even if it doesn't always fully match the live network. Next slide, please. Conformance, that's important. And conformance to standards is a very typical contractual requirement. When buying a new, in this case, thinking of buying a mission critical network or mission critical service, you'll probably put in your contracts it has to meet certain standards A, B, C, etc. And what comes to interoperability, interworking, you probably would say in those reference points Dave was talking about earlier would be the ones you have to prove that you're the conformance to standards on those. It's a basis for interoperability, obviously, but for people who have been around mission critical comps over the years, realize that it's great that someone is actually done something according to a standard, but it doesn't necessarily mean that two products interoperate. So it's a good basis, and it lowers the risk for or amount of case-specific modifications when you start plugging things together, but you might still have some, so just keep that in mind. And to do tests, you need test cases. You could create your own if you're an operator, and obviously you want to base those on an IWF 1, 2, and 3, defined by 3GPP. And who knows, we might get a nice set of test specs from there. But maybe you want to think about it a bit wider. If you start testing these things, yes, you are testing the interface, but in the end, what you are really interested in is the end-to-end performance and functionality from LMR radio to MCUE. Does that work? But on the other hand, that would be a huge test set. So you probably want to consider and think about how much of the other functionality that needs to be tested or proven to work as you expect, or whatever terms you would want to do there. So when you scope your conformance test set requirement, then think about that as well. And one more slide, please. And while I was speaking a moment ago about doing the conformance test yourself, maybe that's not actually your job as an operator. Maybe it's much better to have formal conformance testing done by someone else. So, but first, do we really need this? As I said, interoperability is the interesting thing in the end. Yes, I think this is definitely worth doing. For the PPDR, public safety operator, as I said, it's less local testing that you expect to do after that. And something has been proven to work to standard. It's a good starting point. For the supplier side, there's this big potential benefit. You prove your product works, you have certificate for it. So basically that should be enough for all of your potential customers instead of having to go to everybody and test it again and again and again. So test once, sell globally. Although life isn't that simple. Software gets improved over time, especially in modern times where everything's agile. You get new functions once a month, twice a month even. How often should you go and run a formal performance testing scenario? Every time your version changes, even the last digit, or maybe only when bigger version changes happens? Well, that's something to consider when you're a supplier. Maybe you want to do it every time there's a new procurement ongoing, so you have fresh certificate waiting for to be shown to the potential buyer. Up to you. But on top of that, security patches. We obviously don't want to see many security patches. We'd like to see very secure, reliable solutions, but still, they might happen. Security holes open up all the time, and they come pretty unannounced, so you might want to roll out those very quickly. Maybe you can't afford to wait for formal conformance testing to happen. And then the last thing is that I see a need for a trusted independent test authority to run these tests, or at least witness them and give a stamp of approval that yes, this was done properly, no one cheated, you can really trust this certificate. The challenge there is that whereas in Tetra, the Tetra Association, as TCCA was known earlier, was a perfect party to set up this environment for Tetra interoperability testing. When talking about conformance testing for interworking function between several technologies, all standardized by different organizations, there probably isn't any association or company who is capable of doing all of this today. Maybe this is something for TCCA to take care of one way or the other.
Brings us to the end of today's event, which I hope you found valuable and interesting. Before closing, I'd like to remind you to register for Critical Communications Week, our online event for 2020, which takes place from the 2nd to the 6th of November. You can find all the details and register for free at criticalcommunicationsweek, all one word, .com, as shown on this slide. So please do take a look and join us for the Critical Communications event of the year. So all that remains now is for me to thank again our presenters very much on behalf of you all, as well as TCCA. Please everyone, let us have your feedback afterwards, but for now, goodbye, stay safe and well. Thank you.